Hello students, welcome to today's lecture. Okay, today we are going to discuss equation of motion. Okay, so equation of motion is nothing but the momentum balance. Previous lecture we discussed the mass balance. We derived it. Okay, so in this lecture we are going to derive the momentum balance equation. This is very similar to the momentum shell balance of the previous chapter. Okay, so only difference is we are going to take into account the accumulation term as well. Okay, so earlier we did this balance only, right? Rate of momentum in minus out plus external force equal to 0. So earlier we assumed that there was no accumulation, so this was assumed as 0. Fine, but in this lecture we are going to derive the momentum balance equation in general, which is applicable to any problem. Okay, so the general equation we're going to derive in this lecture. Okay, so let's start it. So you have to use this equation only. So rate of increase in momentum means momentum accumulation, rate of momentum in, rate of momentum out, then external force on the fluid. I already told you the units are force, Newton, right? Because this is rate of increase of momentum, but the units are rate of momentum, right? Rate of momentum is nothing but force. Same here, this is force units, this is force units. Okay. Now, to derive this, you have to assume a small, control volume. So you have to assume a small control volume. Okay. So I'm using, rectangular coordinates. Rectangular coordinates. Okay. So definitely, as in mass balance, we took this coordinate system x, y, z. Okay. You can derive this equation of motion using cylindrical coordinates as well. Okay. Okay, so the derivation is very simple in the rectangular coordinates. Okay, so we'll go with this. Okay, so you are assuming a small finite volume, very small volume. Okay, delta V. What is the volume of this small element? That is delta X, delta Y, delta G. Okay, so in this direction it is X, so it is delta X. In this direction this is Y, so it is delta Y. So in this direction it is delta G. Okay, so you have to find the rate of momentum in and out, right? So you have total of how many terms? 3 terms, total of 9 terms, because this is a tensor. Okay, so you have a total of 9 terms. Okay, so it's like saying I have 9 terms, like phi xx. So fix the x first. This indices is the momentum transfer direction, right? And sorry, this is the velocity direction and momentum transfer direction in this. Okay, so this first index is velocity direction. Okay, but the transfer direction is in this direction. Okay, similarly we'll have phi fix y, 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 so x, y, z. The fluid is flowing in y direction and momentum is transferred along the other directions. Okay, and thirdly phi fix z, x, y. So the velocity is in the z direction, fluid is flowing in the z direction, and momentum is getting transferred in x, y, z direction. Okay, so we have total of how many terms? 3 terms, 3 and 3. 3 into 3, 9, right? So instead of doing all the 3 transfers together, I will do momentum, momentum transfer balance for a particular direction. So this is x direction, right? So see, the fluid is flowing in x direction. So momentum is getting down in this direction. So I will try to do the balance of x momentum first. Okay. So x momentum, this is x momentum, this is y momentum, this is z momentum. So firstly, I will do the momentum balance for x direction. Then I will do for the y direction. Then I will do for the z direction. Okay. Once I have done that, I will express this all balances in the vector form. Okay. Okay. So firstly, we'll do the x momentum transfer. Okay. So the momentum is in x direction, but it is getting transferred in x, y, z. So I will first do the balance in x direction. So I will do the balance for the x momentum first. Then we'll go for y momentum. Okay. So if you see this figure, right? So we have three terms total, right? So phi xx. So for phi xx, phi is what? Combined momentum, right? So molecular transfer plus convective transfer. Okay. I already told you that. So if you don't know it, so go study it, then come back to this lecture. Okay. So for x momentum, I have three phi values. So phi xx. So x momentum is transferred in x direction. See, this is x direction. Okay. And phi zx, this is x momentum transferred in z direction, right? And we have this phi yx, x momentum transferred in y direction. Okay. So let's do the balance. So what is the accumulation term? Okay, we'll come to that later. First do the rate of momentum in, right? So what is the rate of momentum in this direction? So we have phi xx, x momentum transfer in x direction at what phase? X phase. This is the x phase, right? And what is this? X plus delta x phase. So this is out. X plus delta x, right? In minus out. Okay. Similarly, phi where to transfer in x momentum transfer in y direction at which phase? At this phase, right? This is the origin is starting here. So this is your y phase. This is in. Okay. This is in. This is out. If you can see the arrows, this is in. This is out. Similarly, this is in. This is out. So this is in minus phi yx at y plus delta y. Okay. And again, the last term in z direction, zx at phase z. This is the z phase minus phi z x at z plus delta x. Okay. This is the rate of momentum in and out for all the three directions. Okay. Then what is the force? I have to calculate the force. So here the force is only will be active is gravitational force, right? So you have to calculate mg, right? Plus mg. So g is the gravitational acceleration due to gravity. What is mass? Mass is nothing but rho into delta vg, right? What is the volume of this element? Small element. So this is delta x, delta y, delta z, because we're using rectangular coordinates. So we have delta x, delta y, delta z, and rho g. This is nothing but force due to gravitation. Okay, or force due to gravity. Okay. If you move down, okay. So you can find here. So yeah, in minus out, right? In minus out at y faces, in minus out at z faces. Okay. Now phi xs is what? It is a momentum flux, right? So kg meter per second, this momentum flux second, right? So we are doing the momentum rate balance. So you have to multiply with, you have to cancel out this term area. So you have to multiply with area. So now if you see the diagram, what is the, so I will consider phi xx, right? What is this area? This is nothing but this length into this length, right? So that is nothing but delta y, delta z, okay? So this is same for this as well, okay? What is this surface area? This is in y direction, right? So this is nothing but delta length into height. So length into breadth. So delta x, delta z. Okay. So this is same for this surface also. Okay. And thirdly, this surface and the bottom surface, right? So that is nothing but delta x, delta y. Okay. So if you multiply with delta y, delta z, then you will get it is rate of momentum. Similarly, you multiply with delta g, delta x, you are getting rate of momentum, right? And this is your force. So you see, g, the acceleration due to gravity, is a vector, right? Because this is acceleration. So it has three components: gx, I cap, gy, j cap, gz, k cap, right? Now, since we are doing the balance in the x direction only, x momentum, so we have to consider only gx. That's why it has given gx here. So you don't consider whole thing, okay? Because we are doing component balance for each direction. So first we are doing the x direction, then we'll come to y direction, then the z, okay? So we are doing x momentum balance. So we have to consider only the components in the x direction. So this is a component in x direction, okay? It's a force due to gravity, okay? So then what is the accumulation term? So we are considering x momentum, right? So if you multiply rho with Vx, so what is this thing? So if you see the dimensions, so kg per meter cube, right? And velocity is meter per second, right? So this is nothing but momentum, right? So I want rate of momentum. So you need delta t here and you have to multiply with volume, right? Yes or no? Then only if you multiply with volume, then this volume cancels out. Then only this delta t will give you second. So it is rate of momentum. Okay, we are doing rate of momentum balance only. So the accumulation term will be, what will be the accumulation term? So accumulation term will be your do rho Vx. We are doing only in x direction. So we have to consider Vx. Y do t, and you have to multiply with the volume, delta x, delta y, delta z, right? Okay, so if you put all these values in the equation, what you'll get? So let's put it in this book. It is directly given. So on this side we will have delta accumulation, delta y, delta g, rho Vx, dou t. This is momentum rate, and here we have delta g delta y phi xx at phase x minus phi xx at x plus delta xx. Similarly, for phi yx and phi zx, right? Now you have to divide by this thing on both the sides. Okay, so what you'll get? So rho x dou t equal to, I will show only the first term. This is phi xx at phase x minus phi xx at x plus delta x. Similarly, you have y. So here it will be divided delta x, right? And similarly, you divided by delta y, and lastly, you will be divided by delta z. Okay. Now, if you take limits, right? Delta x tends to 0, limit delta y tends to 0, then here limit delta z tends to 0, then what you'll get? See, I already told you the derivative formula, right? So fx plus delta x minus fx divided by delta x. Then if you take the limit, then only it is df by dx, right? But here it is swapped, right? So if you take out the minus, then this will become minus and it will pass, and you will get minus out. So you will get exactly dou by dou phi xx, right? So if you rewrite it after taking limits, you get here minus dou by dou x phi xx plus dou by dou y phi yx. So minus is common, plus dou by dou z phi zx. Okay, plus rho gx, and here have rho vx by dou t. Okay, so if you move down, okay, so you have got this, right? This formula, okay, in x direction. Similarly, you can do this balance in y direction. You have to repeat the same steps, only you have to take, only the thing change will be, so instead of vx it will become vy now. Okay, and now you are taking care of y momentum, so you have to only consider this thing. So y x y g, these three terms in and out. Okay, so you'll get x y, here you'll get y, here instead of x you have to replace y and zy, and this will become y, right? So similarly you can do the balance for z momentum, right? So it will become vz, here in the z, the z momentum by z transferred in x y z, right? So here you will get xz, here phi you will get yz, here you will get zz, right? So you have to do this balance for each direction, right? So you'll get three equations. Okay, so similarly you can, so similarly you'll get, sorry, this for y direction, this for z direction. Okay, So you can write in scalar notation. So using only components. So you see you have to replace I. So this is nothing but what? Dou by dou x phi x z, this, right? This is nothing but, this is divergence. Okay, divergence of phi for particular direction. So if you fix the I direction, that means this is fixed, right? And this are there. So you're taking the I component of phi. So this is I component. So you can replace x, x, x. So x component, y component, you have to replace y, 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 right? For z component, you have to replace I by z, 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 right? So this is minus divergence of the phi for each direction, okay, and rho gi. So I can take the values y, x, y, g. Okay, this is your scalar notation or vector notation, because we're doing for, you know, one direction, because it is tensor. So you can express this in the vector term, vector form. So this will give you this vector form. Okay, so you have derived this equation. This is nothing but, you know, momentum, equation of motion or momentum balance. Okay, now you can plug in the values of phi. What is phi? Phi is like molecular transfer plus convective transfer, right? What is the molecular transfer? So P plus tau. If I am taking xy, so xy, this is the molecular transfer, and rho vx, rho vy, right? But in general, if I say ij, it will be P plus tau ij plus rho vi vj. Here it will be Kronecker delta ij. I told you, right? Kronecker delta ij. If you are taking I equal to j, that is, let's say 1, 1, then the value is 1. If I have I not equal to this, let's say I take Kronecker delta 1, these two are not equal, so it will be 0. So the pressure term will not be there for shear stresses, okay? So shear stress, no, I mean the pressure is on x only in normal direction, right? The surface direction should be in the same, as well as the force direction should be same. Then only the pressure will exist. So this, the Kronecker delta ij will become 0 for I not equal to j. So only the pressure terms will be there for this direction, xx, yy, and zz. Okay. So if I put this general formula in this equation, then you'll get final this equation. Okay, you'll get this equation. This is in vector tensor form. Okay. Okay, so now let's go term by term. What are these? So this term I already told you, it is the rate of increase of momentum. Okay. So since you divided by volume on the both sides, so it is per unit volume. Okay. While taking the limits, you divided by the volume delta x, delta y, delta g on both the sides, right? So this is nothing but per unit volume. So this is rate of accumulation, right? So, or you can say, since this is positive, so you can say increase of momentum per unit volume. Okay. Here, this is nothing but convective transfer, right? Rate of momentum addition by convection. Okay. Per unit volume. Everything is in per unit volume. So this is nothing but rate of momentum addition by molecular transport, right? These two actually. These two are molecular transfer. And this is your external force per unit volume. Okay. This can be any external force. So in this case, it is gravity. Okay. So this is your equation of motion. Okay. Definitely you can simplify this. So we'll come to that part where it is called Navier-Stokes equation, when it is called the Euler equation, when it is called the Stokes equation. Okay. So we'll come to that part later. So for now, this is your equation of motion. Okay. So this is the general equation you can apply to any problem. Okay. Just you have to simplify. So for now, let's say generally you do steady state balance. Okay. So this term will become zero. If you're doing steady state balance, there will be no accumulation, right? So you can directly strike off this term to zero. Okay. Suppose there is no convection, so you can directly give zero. Suppose there is no, gravity. If you are considering flow in a horizontal pipe, then there will be no gravity, right? Even if there is gravity, it will cancel out. So this term will become zero. Okay, so we are only left with this. So you can make assumptions to this equation and you can, simplify it accordingly. Okay. Now we'll see these equations in other coordinate systems. Okay, in cylindrical as well as spherical, how they are expressed. You don't have to derive this equation in cylindrical and spherical coordinates. However, there are equations available. You can memorize them. Okay, so we'll go through that. Okay, so these equations are given in the appendix B of the book. Okay, so first we already discussed the Newton's law of viscosity, right? This was the formula. Okay. So this was the formula we already discussed. Okay. So if you are using Cartesian coordinates, rectangular Cartesian x, y, z, so tau x's is nothing but this one, right? Tau y is nothing but this one. Okay. And tau zz is nothing but this one. And tau xy and yx is equal because they are symmetric. Okay. Similarly, this one. So these are the general equations and the divergence of the velocities. Earlier in the momentum shell, we did not consider this part, right? Why? Can you tell me why this part was considered zero? We did not take this into account earlier during shell balance because for I already told you for from mass balance, the continuity equation, if we have density constant or incompressible fluid, then this term is zero, right? So these terms become zero for all the incompressible fluids, or density is equal to constant. If density is constant, then you can directly strike off this value zero. This will make very simple. Okay. And also I told you this directly comes from this only. Here, let's say for falling film problem, we have this z direction, right? This was vz, and it was a function of x only. Okay, because we were considering fully developed flow. So if you do vz by, so consider this part, vz by dou x, so this term will be there. But what about this? This will be zero because there was no flow in the x direction. Okay, in this direction there was no flow in the. We are talking about the falling film problem. Okay, so this term will be zero. So ultimately you will get tau zx equal to minus mu dou vz by dou x. Okay. So if you consider this term, dou Vz by dou y, see the Vz is not function of y. It is only a function of x. So it will become 0. Again, Vy, you know, Vy is direct 0. There was no flow in y direction. So this whole term will be 0. And so on. So you can simplify. These are the general equations. You can apply to any problem. Okay. So we'll resolve the problems we discussed earlier using this equation of motion. It becomes very easy. It's very easy to solve those problems. It reduces the time also. Okay. So we'll move on. So this is the Newton's law of viscosity in cylindrical coordinates. Okay. So you can, again, these terms will be 0 because we are dealing with the constant density fluids, okay, or incompressible fluids. Okay. And other values of tau you can calculate from these formulas. Okay. So this formula will be very useful while solving in cylindrical coordinates, like flow through a circular pipe or flow through a circular pipe in horizontal. This was in vertical direction, this is horizontal. So you can easily solve this using these equations. Similarly, in spherical coordinates, in spherical coordinates we haven't solved the problem yet, but I will try to show one example. Okay, so you can similarly use these equations. If rho is constant, this will become 0. This will become 0. Other values you can calculate. Okay. So this is law of heat transfer. We will come to this when we will study the heat transfer. Now, equation of continuity, we already derived it, right? This was the equation. So if density is constant, so density is not changing with time, it's constant, and this rho can be taken out, so you have got this equation. Right? So divergence of velocity vector is 0 for constant density fluids or incompressible fluids. Okay, so remember this. So in Cartesian coordinates, you can do it. This is in cylindrical coordinates. This is spherical coordinates. Right? You can memorize the formula. Okay. In fact, you have to memorize the formula because they are not going to give you the formula during the exam. So you have to memorize it. Okay. Now we just derived the equation of motion, right? In terms of tau. Okay. So you can, ignore this part. This is for substantial derivative. I will teach you what this means, okay, in the upcoming lecture. Okay. So you focus on this part only. So if you rewrite the equation of motion we have derived so far, so in this term, only the convective term has been transported to this side. Okay. So this is in x direction, this is in y direction, this is in z direction, and it is Cartesian coordinates. Again, if you use cylindrical coordinates, then this is r direction, this is theta direction, this is z direction. So you can use these formulas. And spherical coordinates, this r direction, this is your theta direction, this is your phi direction. Okay. So if you see this formula, it is in the terms of tau only, right? So tau. Okay, you can express this in the velocity terms. Only you have to plug in the velocity tau relation, right? How tau is related, that formula from Newton's law. I already discussed here, right? Yeah. You have to use these formulas. If you're using cylindrical coordinates, use this definition of tau to find out the velocity, right? If you're using spherical coordinates, use this formula. Okay. So this was in the tau. This is only given in the tau terms. Okay. And you can have in terms of velocity. See, here it is assumed that the density and the viscosity is constant. Okay. So if you consider density incompressible fluid and mu is constant, that means mu is constant, it's not function of something, and it is a Newtonian fluid. Newtonian fluid means it obeys that Newtonian fluid formula, that is shear stress, the relation of shear stress with the velocity as given by Newton's law. Okay, if you follow that, then these are the equations for Newtonian fluid with constant density and constant viscosity. Okay, this is in cylindrical, this is in rectangular coordinates, this is in cylindrical coordinates for all three components, this is in spherical coordinates for all three components, okay, in three directions. Okay, so I will show you how to use these equations, while solving problems. We'll rework those problems discussed in momentum cell balance chapter, okay, with the help of this equation. You will see how it's easy to solve these problems using these equations. Okay, thank you.